Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. In this lecture, we're going to introduce the concept of a Taylor and a Maclaurin series. So you should have finished kind of an introduction to power series. So recall that a standard power series is a series of the form summation n equals, it doesn't have to start at zero, but we're going to just go ahead and say that, n equals 0 to infinity, c sub n, and then x minus a to the nth power. That's a power series, what I would call centered at a. Okay, and notice that this is a function of x. All right, so now we're going to grow this idea. You have likely, hopefully, just finished a whole entire topic. If you haven't, you can go back into possibly some videos that I've made to find this topic. But you've really investigated power series representations for functions of this form. So this one specifically sums out to be the summation from n to 0, from 0 to infinity, of x to the nth. And notice the coefficients, those c sub n's here in this formula. Let me go ahead and highlight those. Those c sub n's right there are 1 in this problem, or in this version, and the center is at 0. Anyway, you've just finished a whole section on that and how to manipulate a bunch of different power series that you were handed that relate back to this. But now we're approaching a completely different question. What if our power series cannot be represented that way? That is, what if a given power series cannot be related to that magic form of 1 over 1 minus x, whether it's through differentiation or integration, or a given function can't be written as that. Again, whether it's through integration or differentiation or substitution. What if we can't do that? A typical function like this might be like a sine function, right? The sine of x, you just can't write as a rational function like that as 1 over 1 minus x or 1 over 1 minus something. You just can't do that. So that's a good example. So to make this work, we're going to go ahead and make a couple assumptions. So I'm going to use blue ink here to kind of showcase this. We're going to go ahead and assume that given a function, we will assume that that function has a power series representation centered at x equals a. Now this is a big thing. So like, for example, that sine of x that you see right here, we are first going to start with the assumption that we can find a power series, or that there exists a power series representation for that function centered at a. That is, we are going to go ahead and say that f of x is equal to a summation, let's go ahead and write that in, n equals 0 to infinity, just stealing our notation from previous here, c sub n x minus a raised to the nth power. Now, this power series representation might not work everywhere, but we're centered at a, so we're going to say that this is going to work for x in a minus r to a plus r. So in other words, some neighborhood centered at a, this power series will represent our function f. Okay, so we have made that assumption. That's assumption number one. The second assumption is kind of critical here. Actually, both these are critical. We're also going to assume that all derivatives exist at a. That is, that we know that the first derivative at a exists, the second derivative at a exists, and so on and so forth. And this exists for all n in the natural numbers, and that's what that notation means. So if you want to review that notation, please look it up. It's symbolic logic there. The upside down capital A means for all, and then that little E looking object means that belong to. So for all n that belong to, and the double bar n means the set of natural numbers. Okay, so we're going to assume that all derivatives exist at a, and the function also exists at a. I should also say the function exists at a. So what exactly will this imply then? Well, we happen to know that we've assumed f is equal to this power series expansion, so that f of x is equal to c naught plus c1 x minus a plus c2 x minus a squared plus c3, and so on and so forth, right? And I'm just going to write those three down, but it goes on forever. And what this implies is that f at A, since we've said that f exists at A, is, well, if you take a look at that, all those terms that have x minus a's, those will disappear if you plug a in, and so f of a will just be c naught. Well, that's kind of nice. We just found our first constant. That was very quick, right? And so we could technically, let me go ahead and grab this guy and move him down. We could go ahead and replace c naught with f of a. And now I'm going to go ahead and ask myself, well, then what's f prime at a? Well, f prime itself, if you take a look at this, this guy right here, the polynomial expansion, f prime is going to be, well, we got c1, because that's the derivative of the first term. This guy right here is just 0 because it's a constant. The derivative of the second term, well, that's c1 times x, basically. And so the derivative, that's c1. Then we have plus 2c2 times x minus a, plus 3c3 times x minus a squared. I'll write the next one too, plus 4c4 x minus a to the fourth, and plus so on and so forth down the line. And we know that f prime at a exists because all derivatives exist at a, so let me plug in a into that. F prime evaluated at a, and again, all the terms on the back end here, let me highlight the back end, all these terms end up disappearing, and you get that f prime at a is equal to c1. Well, that's kind of cool. So I'm going to go back up to the original function here. I'll erase that c1, and I'll replace it with f prime at a, and I'm going to put a little 1 factorial downstairs because I'm going to show something in a moment. Okay, now we're going to figure out what f double prime at a is, so we'll need to figure out what f double prime of x is. Well, f double prime of x is equal to, again, the first object here, the first term, its derivative is 0. Second term, its derivative is 2c sub 2. The next guy in line is 3 times 2c sub 3 x minus a to the first. The next guy is 4 times 3 c sub 4 x minus a to the third, plus so on and so forth down the line. And we see that f double prime, again, because all derivatives exist at a, f double prime at a, any term with x minus a in it will disappear. I think I miswrote something here. Oh, I did. Everybody's probably yelling at me. This exponent here is 3. And so this exponent here is 2. Sorry about that. Can't be too perfect, right? Okay, so f double prime at a is 2c sub 2. And if you notice the pattern that's happening with these coefficients, these are factorials, right? 3 times 2 and then times 1. This is 2 times 1. So I'm going to actually rewrite this as 2 factorial c2. And therefore, c2 is the same thing as f double prime at a over 2 factorial. And so all the way back up to the original function here, let me grab that function, make some space here so that I can write it properly. I'll just scoot that over slightly. Okay, and I know that c2 is going to be replaced with f double prime at a over 2 factorial. Now you can probably see the pattern, but I'm just going to do the last one here real quickly. So f triple prime, again, we want to evaluate this at a, but I'm going to take its derivative first. So the derivative of f double prime is going to be, well, derivative 2c2 is gone. The derivative of the next one is going to be 3 times 2 times 1 c3 plus 4 times 3 times 2 c4 times x minus a to the first, plus and so on and so forth down the line. And therefore, f triple prime at a, all the terms with x minus a's disappear, and you get 3 factorial c sub 3. You can argue now via induction what the general pattern is going to be, but I'm not going to do that here. Instead, I'm just going to go ahead and write the result. But we see that the third coefficient, c sub 3, it's actually the fourth technically, but anyway, is f triple prime at a over 3 factorial. So let me replace that here. F triple prime at a over 3 factorial. And in general, again, this can be proved via induction. In general, The nth derivative, or the nth coefficient, is going to be the nth derivative evaluated at a over n factorial. And therefore, if we assume that a function f, all the way at the top here, right here, if we assume that a function has a power series expansion and that all of its derivatives exist, then this version of the function, that guy right there, can be replaced because we now know all the constant coefficients. And so I'm going to write that down below in a clean form. Thus, f of x, this is only if f is equal to its power series expansion. F of x is equal to the summation n equals 0 to infinity, the nth derivative evaluated at a over n factorial times x minus a to the nth power. And that is a beautiful, beautiful result. That means that given a function, you can try to find its power series expansion just by knowing all of its derivatives. Now, something that often gets lost on students, this is if and only if, well, I shouldn't say if and only, it is if f has a power series expansion, and if it's equal to its power series expansion. Okay, so I will go ahead and write that as a definition because we actually define this format as something. Okay, so by definition of a Taylor and a Maclaurin series, these are actually two totally different, not totally, but two different forms of the same power series. The statement is if, and that's a huge if we know that f has a power series expansion at a, then f is actually equal to its power series expansion at a, and it looks like this, right? The summation 0 to infinity of that stuff. A couple things to note. If a is not equal to 0, this is the right-hand side. I'll just write it that way. The right-hand side is called the Taylor series. A little bit of a note here is that all functions have Taylor series expansions at a, but not all functions are equal to their Taylor series expansions at some point a. So that's a very big if. That's where this if comes in. You can find a Taylor series expansion for a function about a point a in most situations. However, it is not always true that the function will equal its infinite Taylor expansion. Okay. Also note that I mentioned here, kind of as on the side note, and I'll highlight this in blue here, that this expansion must hold for x in an interval a minus r to a plus r. R is the radius of convergence, something that you should know already how to find for a series. So this is for x in a minus r to a plus r. There is a slight incorrectness about that notation. The endpoints could be included, or only one endpoint could be included. So I'm just sort of hand waving the notation a little bit, but in reality, when you check for convergence, you usually check the endpoints separately. Okay, so here we go. If a is non-zero, so in other words, we're centering anywhere but 0, then this is called the Taylor series of f at a, and if a happens to be 0, it gets its own special name. I will almost always still call it a Taylor series about 0, but some people call it, most people in fact, call it a Maclaurin series. And note in that part of that definition, I don't even say it's a Maclaurin series of f at 0. It's just called the Maclaurin series, a special case where you center at 0. So most series that you're going to see in differential equations and really in mathematics are going to be Maclaurin series, but almost everybody still calls them Taylor series because that's the general case. It's just easier to say Taylor series. It's the most popular naming convention for them.